Hello students, welcome back once again to a series of lectures on dual nature. So we will continue from where we have stopped in the previous class. We were trying to understand what photoelectric effect is and how particle nature or particle theory of light was successfully able to explain the photoelectric effect. Okay, let's quickly recall the photon picture of light that we have seen in the previous class. So we have seen that an interaction of radiation with matter. Radiation here means basically the light itself, right? So the light is when light interacts with matter, it behaves as if it is made up of particles called photons. Okay, and each photon has a certain value of energy, and that value of energy is given as E is equal to h nu. E is equal to h nu, where h is the Planck's constant, and mu is the frequency. Okay, mu is the frequency. E is the energy of the corresponding photons. And each photon has an energy, h nu, as we have said, and momentum P is equal to E by C. The momentum of each photon is given by E upon C, or E can be written as h nu upon C, right? So all photons of light of particular frequency or wavelength have same energy and momentum, whatever the intensity of radiation may be. So that's what we have seen. So we have tried increasing the intensity of the radiation as we have seen in the previous uh, class. We have seen using the simulation as well. We tried increasing the intensity and we saw that there was no change in the stopping potential, or there is no change in the energy, the kinetic energy of the emitted photon. Because as we have seen, according to the photoelectric equation, K max, or the maximum kinetic energy of the emitted photon, is given by h nu minus h nu naught, where h nu is the energy of the incident photon and h nu naught is the work function. H nu naught is the work function, which we denote using the letter phi. What is work function? It is basically the minimum energy required to eject out the electron from the metal surface, right? So by increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area, right? So number of photons per second increases as we increase the intensity according to particle theory, and with each photon having the same energy, right? Energy of photon is not increasing in this case, but rather the number of photon is increasing, and thus the number of electrons ejected out will also increase corresponding to that. So photo current will increase, right? Photo current will increase, but for a certain value of intensity, there is a saturation value of current, as we have seen previously. If you recall the graph, so we have seen that if you draw photo current versus photo current versus potential, collective plate potential, you saw that for a certain intensity of light, whatever the potential is, the photo current will have a certain saturation value after after a certain level, right? So certain value, after a certain value, the photo current will become stagnant, the photo current will become steady, right? If you increase the intensity further, more photo electrons will be ejected out, and hence more and more photo current will come up. But again, for a different intensity, you will see that the curve looks like this with a higher saturation current, although you increase the potential, it doesn't matter, right? But if you increase the energy of the incident radiation, or if you increase the frequency of the incident radiation, what happens? The energy of the ejected electron increases. As a result, the stopping potential required will be higher, corresponding to that higher frequency of the incident photon. Okay. Okay, so the photon energy is independent of the intensity of the radiation, and the photons are electrically neutral and are not deflected by electric and magnetic field. That's a very important point. So we are taking the photons to be electrically neutral. They are neutral particles, right? And are not deflected by electric and magnetic fields. And in a photon particle collision, the total energy and momentum are conserved, right? So we have seen this point as well. Energy and momentum is conserved, but the number of photon may not be conserved in a collision. The photon may be absorbed or a new photon may be emitted, right? So because of that, the photon number may not be conserved as such, but the energy and momentum will definitely be conserved in a photon particle collision, like in a photon electron collision. All right. Now let's move to the new topic of today, that is matter waves. It's a very revolutionary idea when it was put forward. So actually, it was when the idea of light or the radiation being a particle introduced, or lit up the idea or brought up this thought that uh, why can't matter have wave nature as well? If radiation can have particle nature, why can't matter have wave nature as well? So actually, French physicist Louis Victor de Broglie put forward this hypothesis that a moving particle of matter should display wave-like properties under suitable conditions. Okay, so the waves associated with moving particles are called matter waves or de Broglie waves. The wavelength associated with a moving particle is known as de Broglie wavelength, because if it's a wave, if there is a wave associated, there has to be an associated wavelength as well. So that wavelength, that associated wavelength associated with a moving particle is called de Broglie wavelength. Okay, that de Broglie wavelength is given by lambda is equal to h upon p. H upon p. This is equal to h upon mv. H upon mv, where p is the momentum, right? P is the momentum. P is the momentum. Okay. Now kinetic energy of the particle, kinetic energy is given by p square by 2m. P square by 2m. Why is it p square by 2m? Because we know kinetic energy is equal to half mv square, right? Kinetic energy is equal to half mv square. So if you multiply with m and divide with m, you can see this becomes m square v square by 2m. So this can be written as p square by 2m, right? Where because p is equal to mass into velocity. That is kinetic energy. So p square by 2m is equal to k, or I can write p square is equal to m times kinetic energy, or p is equal to under root 2 times m times kinetic energy, where m is the mass of the particle, k is the kinetic energy, p is the momentum. Okay, so 2 times m times kinetic energy, or from this equation, I can write lambda is equal to 2mk. How? Because I know lambda is equal to h by p. So p can be written as root 2mk, kinetic energy. Okay, so very important. So you can see here, when a charge is accelerated through a potential difference v from rest. Okay, so if a charged particle here is accelerated from zero potential to some potential difference, or through some potential difference, so what happens? We have studied in the previous chapter, or in the second chapter, we have studied how much work is done, right? So the work done is equal to q times v. Okay, we have seen that where v is the potential difference through which this charge is getting accelerated. So if this is the work done, this work is entirely stored as the kinetic energy of the particle, right? This work is stored as the kinetic energy of the particle. So kinetic energy of the particle is, kinetic energy is equal to this work done. So this is k is equal to q into v. So we know lambda is equal to h by p, de Broglie wavelength. This is equal to h by root 2mk. K is the kinetic energy, or kinetic energy can be replaced with 2m q into v. Okay, very important. Where m is the mass of the charged particle, and q is the charge of the charged particle, and v is the potential difference through which it is getting accelerated. Now here in this example, you can see that we are trying to calculate the de Broglie wavelength of an electron. Okay, we know mass of the electron is given by 9.1 into 10 power minus 31 kg, right? This is the mass of the electron. And the charge of the electron is 1.6 into 10 power minus 19 coulomb, right? So if you calculate it, if you put the values in this equation, you can see that we will get after substituting for h, m, q, and all, we'll get the value for lambda as 12.27 upon root v, where v is the potential difference. This much Armstrong will be the wavelength, the de Broglie wavelength associated with an electron which is accelerated through a potential difference v. You can see it depends on v, right? Okay, now you can see a question here. It's a very common question. An electron is accelerated from rest through a potential difference of v volt. If the de Broglie wavelength of the electron is 1.227 into 10 power minus 2 nanometer, the potential difference is. So clearly we have seen this equation above. Lambda is equal to 12.27 upon root v. This much Armstrong. So this value, lambda, it's given here. This is 1.227 into 10 power minus 2. You can substitute that from that equation. You can find the value of v. So if you substitute this 1.227 into 10 power minus 2 nanometer is equal to 12.27 by root v Armstrong. Okay, now this to convert both sides into Armstrong, so I'll multiply and divide with okay, but let's do one thing. Let's write this nanometer as 10 power minus 9. Okay, so this nanometer I can write it as 10 power minus 9. So I will do 10 power minus 9. Okay, and this Armstrong I can write it as 10 power minus 10. Minus 10. Okay, so I can take this to the other side. So this becomes root v is equal to 12.27 into 10 power minus 10 divided by 1.227 into 10 power minus 11. Okay, so again this can be written as 12.27 into 10 power 11 minus 10, so it's 10. So divided by 1.227, right? So if you square both sides, finally you can get the value for v. So you can see here, finally I'm getting the value as 10 power minus 10 power 4. So 10 power 4 volt is the answer here. 10 power 4 volt. Fine. Okay. So option D is the correct answer. Option D. Okay. Now let's look at some of the questions which is important from the board perspective, previously asked in the CBSE board examinations. So the work function for a metal surface is 4.14 electron volt. The threshold wavelength of this for this metal surface is. So what is given? The work function is given. Work function phi is given. Work function phi is defined as h nu naught, where nu naught is the threshold frequency. But they are asking for the threshold wavelength, right? So we can replace this in terms of wavelength, hc by lambda naught. So I can write this as lambda naught is equal to hc by phi. hc by phi. H is 6.63 into 10 power minus 34 into c is 3 into 10 power 8 divided by what is phi? 4.14 electron volt. 4.14 electron volt means 4.14 times 1.6 into 10 power minus 19 joules. Okay, so after solving this, you will be getting an equation. You will be getting an answer of around 3000 Armstrong. Around 3000 Armstrong. Okay, so that is the threshold wavelength of this metal surface. So what do you mean by threshold wavelength? The wavelength above which you won't be wavelength of incident radiation, above which you won't be able to observe a photoelectric effect. Or photoelectric emission won't happen for the incident radiation having wavelength more than this value. What is threshold frequency? The frequency of incident radiation below which threshold, below which the photoelectric emission is not possible. Okay. Again, we have a different question. Again, this is also a PYQ from board. So a proton and an alpha particle have the same kinetic energy. The ratio of de Broglie wavelength associated with the proton to that of the alpha particle. So what is the equation for de Broglie wavelength? We know lambda is equal to h by p, right? H by p. Or I can say lambda is equal to h by p can be written as mass into velocity. Or in terms of, if you want to write in terms of kinetic energy, because the question is in terms of kinetic energy, we can write lambda as lambda is equal to h by root 2 times m k. K is, m is the mass and k is the kinetic energy. Okay. Now we are asked the ratio of de Broglie wavelength associated with proton to that with alpha particle. So you need h. H is a constant, so it's clear. We need mass, we need kinetic energy. So kinetic energy is a constant, right? So we can rewrite this equation as lambda of proton is equal to h by root 2 times mass of proton times kinetic energy of proton, which is same as kinetic energy of alpha particle in this question. So I'll write it k itself. So lambda of alpha particle will be h by root 2 times mass of alpha particle into k, kinetic energy. So the question is to find the ratio. So lambda p upon lambda alpha is equal to h upon root 2 m k by h upon root 2 mass of alpha particle times k. So h cancelled out. This becomes root 2 m alpha k by root 2 mass of proton times k, or this is mass of alpha particle by mass of proton under root. So what is mass of alpha particle? Mass of alpha particle is actually 4 times mass of proton divided by mass of proton. So this becomes root 4 is to 1, or you can write it 2 is to 1. So 2 is to 1 is the answer. So we have option number 2, right? 2 is to 1. So the question is to find the de Broglie wavelength associated with the proton to that of alpha particle, ratio of de Broglie wavelength of proton to that of alpha particle, right? Next question, again a board PYQ. How would the stopping potential for a given photosensitive surface change if the frequency of incident radiation were increased, right? So we have already seen what is stopping potential, right? And we have already seen what is how it is affected by the frequency, right? So we have seen that if the frequency of incident radiation is increased, clearly the stopping potential will also increase. Stopping potential will also increase, right? So we have seen that in a graph like this. So for stopping potential versus frequency, the stopping potential will start to increase once the frequency is above a certain value of frequency, which is called the threshold frequency. Above that, the stopping potential will linearly increase with frequency like this, right? So the frequency of the incident radiation, if it is increased, then clearly the stopping potential required to stop it will also increase because the kinetic energy is increasing. So you can write it like this. As the frequency of incident radiation is increased, the kinetic energy of the emitted photoelectrons also increases. So the stopping potential will also increase, will increase. It's very obvious. Why? Because the stopping potential is the potential required to stop the most kinetic, most energetic photoelectron from reaching to the collector plate, right? So if the emitted electron is having more energy, so it will be requiring more potential to stop it, more negative potential to stop it from reaching to the collective field, right? So, and that's also evident from the, you know, Einstein's photoelectric equation, which tells you that K max is equal to h nu minus phi, h nu minus phi. So this phi is a constant for a certain material, right? And threshold I mean the work function, and the threshold frequency is also a constant. So if you increase the frequency of the incident radiation, that is this nu, that means this term becomes more and more larger. That means the kinetic energy term will become more and more larger since phi is a constant. Okay, and hence the stopping potential will also increase. Now, coming to the second question, how would the stopping potential be affected for a photosensitive surface if the intensity of incident radiation were increased? So, second part, as intensity increases, as intensity increases, number of number of photons increases, number of incident photons increases, and hence number of I'll write with a different color. Number of incident photons increases, and hence the number of photoelectrons emitted, photoelectrons emitted will also increase, But that doesn't mean the stopping potential will increase. Why? Because stopping potential depends on how much potential is required to stop the highest, most energetic electron which is coming out. But the energy of the emitted photoelectrons are not changing because the energy of the incident light is not changing. Because according to this photoelectric equation, the kinetic energy of the emitted photoelectron depends only on the frequency of incident radiation, right? And the work function. So since neither of them are changing, we can say the intensity, uh, if it is changing also, it's not affecting the stopping potential, right? So it's only affecting intensity increasing will only change the number of photoelectrons emitted or number of photons coming in, and hence number of photoelectrons emitted, and hence the photocurrent increasing, right? It does not affect the stopping potential, or it does not affect the kinetic energy of the emitted photoelectron, right? Next question. A light of frequency nu is incident on a metal surface whose work function is W naught. So the work function is given as W naught, right? And the kinetic energy of the emitted electron is K. Okay, kinetic energy of the emitted electron is K. If the frequency of incident light is doubled, then the kinetic energy of emitted electron will be, right? We know from photoelectric equation, we can write kinetic energy K max will be equal to, uh, we can write K max as the energy of the incident photon minus the work function of the metal, right? So in this case, in the first case, they are saying kinetic energy of emitted electron is K, and the kinetic energy of the emitted electron is K in the first case, and they are saying the frequency of the incident radiation is nu. So the energy of incident photon will be h nu, and the work function is W naught, right? And in the second case, they are saying if the frequency of incident light is doubled, what is the kinetic energy? So let's say the new kinetic energy is K dash. Now what they are changing is the frequency is doubled. So this becomes 2 times the initial frequency minus W naught, because it's the same material. Hence the work function will not change, right? So K dash is equal to 2 times h nu minus W naught, right? So you have to say the kinetic energy is whether it is 2K, whether it is more than 2K, between K and 2K, or less than 2K, right? Here it was, here the K value was h nu minus W naught, right? H nu minus W naught, or I can write this as h nu uh, plus h nu minus W naught, or because it's 2 times h nu, so I can write this term as K plus h nu. So clearly, as the frequency is doubled, K dash, the kinetic energy is also getting increased. So you can say it's more than K, more than K. Is it uh, less than 2K? What do you think? Right? There is an option. It's more than K. There's an option, but is it between K and 2K? Right? Sorry, there is an option which is more than 2K, but there is also an option for between K and 2K. What do you think about it? Okay, so to understand why whether it should be greater than 2K or whether it should be K between K and 2K, we will have to convert this h nu in terms of K. Okay, so that's what we will have to do. So what we can do here is we can replace this h nu with K in this equation. So we'll just rewrite this equation here. Uh, so we will make slight corrections over here. Okay, now we can write the new kinetic energy as K dash is equal to 2 times h nu because the frequency is doubled minus the work function. So this h nu can be replaced from this equation. I can write h nu is equal to K plus W naught. So I can replace the h nu with K plus W naught here as well. K plus W naught minus W naught. So this becomes uh, 2 times K plus 2 times W naught minus W naught. So this is 2K plus W naught. Okay, so clearly it is something greater than 2K. So clearly our option has to become option 2. From the first way that we did, so it was not clear whether it is uh, greater than 2K or whether it is between K and 2K. Okay, so this way it's very clear. So I hope it is clear. Okay, so then here is a homework question for you. So the variation of stopping potential with frequency of the incident radiation for 4 metals are given, right? For the same frequency of incident radiation producing photoelectrons in all metals, the kinetic energy of photoelectron will become maximum for which metal, right? So the frequency of incident radiation is same in each case, but the difference is the we are taking different materials, right? We are taking actually 4 different metals. So clearly, according to what we have discussed previously, their work functions are different. That is why you can see the stopping potential is increasing after different points of frequency, right? For metal A, you can see the threshold frequency is less compared to B, C, D, right? For B, the threshold frequency is greater than A, but less than C and D. So similarly for C and D as well. You have to find for the same frequency of incident radiation, which for which metal the kinetic energy of photoelectron will be maximum. So this one I'm giving you as a homework. You can try it. Okay, and we will discuss this question in the next class. So in the next class, we'll be having a one short discussion on this chapter. We'll discuss from the beginning. We'll go through the whole chapter once again so that there will be better clarity regarding it. Okay, so we'll continue again. We'll meet again. Thank you. Bye bye.